Welcome to video 8 in my rotational motion playlist. The title of this video is Rotational Energy. I'll briefly review conservation of energy. Next, I'll discuss the formulas for rotational energy. And finally, I'll solve 4 carefully selected example problems step by step. Let's begin by reviewing conservation of energy. It's never a bad idea to review important concepts in physics, even if you're already familiar with them. Conservation of energy means energy is neither created nor destroyed. The amount of energy in the universe is constant. Energy can change forms from potential energy to kinetic energy, but the total amount of energy can never change. This animation from the University of Colorado's PhET is a great visualization of energy conservation in action. We can imagine energy as coming in small cubes. There can be a cube of mechanical energy, electrical energy, thermal energy, light energy, or chemical energy. There's a finite, though very large number of energy cubes in the universe. They can't be created or destroyed, but they can change color as they transform from one type of energy to another.
The boy gets chemical energy from food, which came from the sun. As he pedals, that energy turns into mechanical energy, spinning the wheel. The wheel drives a generator, which resists motion, so mechanical energy is converted into thermal energy, heating the water. When the boy runs out of energy, he has to eat more to keep going. The sun ultimately powers all of this through nuclear fusion.
The unit of energy is the joule, named after the scientist James Prescott Joule. A calorie is another unit of energy not used by scientists. 1 calorie equals 4.18 times 10 to the third joules. A pint of beer has roughly 8 times 10 to the fifth joules. A small stick of M80 dynamite has 2 times 10 to the fifth joules. And a slice of pizza has the energy of about 10 small sticks of M80 dynamite. When you eat the pizza, the energy is released slowly. You don't explode, although you have to exercise or you'll get obese. On this slide, I want to discuss the formula for the kinetic energy of a rotating body. To calculate the kinetic energy of a rotating object, we divide it into many small mass elements and sum the kinetic energy of all the masses. The total kinetic energy is equal to the sum of the individual kinetic energies. Kinetic energy is 1/2 mv squared. For a rotating object, v equals r omega, and v squared equals r squared omega squared. This leads to the important formula for the kinetic energy of a rotating object. Kinetic energy of rotation equals 1/2 I omega squared, where I is the moment of inertia. When an object is moving through space, it can have both rotational as well as translational kinetic energy. In general, the kinetic energy of an object is equal to the sum of the kinetic energy of the rotation of the object plus the kinetic energy of the translation of the object. 1/2 mv squared, where v is the velocity of the center of mass. And of course, we all know the potential energy due to gravity is equal to mgh. Now I have 4 example problems to go through. Question number 1. A heavy flywheel is designed to store a large amount of rotational energy. Suppose the flywheel is a solid disc with a mass of 200 kilograms and a radius of 30 centimeters, spinning at 1,000 revolutions per minute. Here's a video to help with the visualization. A. Calculate the rotational kinetic energy of the flywheel. B. At what speed would a 1 kilogram particle need to travel to have the same kinetic energy? Rotational kinetic energy equals 1/2 I omega squared. The moment of inertia of a cylinder is 1/2 mr squared. The mass was given as 200 kilograms. The radius is 0.3 meters. The moment of inertia is 9 kilograms meters squared. To get omega, the angular velocity, we have to convert from revolutions per minute to radians per second. 1,000 revolutions per minute equals 104.7 radians per second. Kinetic energy equals 1/2 I omega squared. Plug in the values. And the disk has a total rotational kinetic energy of 4.93 times 10 to the fourth joules. A 1 kilogram particle weighs 2.2 pounds. Kinetic energy equals 1/2 mv squared. For a 2.2 pound object to have this value of kinetic energy, it has to be moving at 314 meters per second, which is over 700 miles per hour. Question number 2. A thin hoop is rigidly attached to a light rod. The assembly is held upright and can pivot about a horizontal axis at the bottom. The system is released from rest and allowed to swing freely under gravity. What is the angular speed of the assembly about the pivot as it swings to the upside down position? So this question is saying there's an object like a tennis racket. It's rigidly attached to a rotation axis. When you let go of it, it's going to fall to the upside down position. What's its angular velocity at this location? To solve this problem, we're going to use conservation of energy. We have to begin by calculating the center of mass of the object so we can find the change in potential energy. Calculate the center of mass of this object about the rotation axis. We take the mass of the rod times the location of the center of mass of the rod at L/2, and we add it to the mass of the hoop times the location of the center of mass of the hoop at a distance of L plus R from the rotation axis. And that gives us a center of mass of the whole object 1.375 meters above the rotation axis. As the object falls from this location to this location, the center of mass moves 2.75 meters down, and the potential energy of the system decreases. We'll also need the total moment of inertia of the object. We can calculate that by adding the moment of inertia of the rod to the moment of inertia of the hoop. The moment of inertia of a rod rotated about one end is 1/3 ml squared. The moment of inertia of a hoop about an axis through its center is 1/2 mr squared. The distance from this rotation axis to the center of the hoop is r plus L. We can use the parallel axis theorem and find the total moment of inertia of the system is m times 4.875. To solve this problem, we use conservation of energy. The change in potential energy plus the change in kinetic energy equals to 0. This tells us that the negative change in potential energy is equal to the change in kinetic energy. The final kinetic energy is 1/2 I omega squared. The initial kinetic energy was 0. Change in potential energy is mg delta y, where delta y is 2 times 1.375. That has to equal to 1/2 I omega squared. We calculated I on the previous slide. This tells us that omega, the angular velocity of the tennis racket when it falls to the bottom, is 3.33 radians per second. Question number 3. Two solid spheres of identical mass and radius are released from rest at the top of an inclined plane with the same height h and angle theta. One sphere rolls without slipping down a rough incline. The other sphere slides without friction down a smooth incline. Question A. Find the ratio of kinetic energies at the bottom. This is the ratio of the kinetic energy of the ball that slid divided by the kinetic energy of the ball that rolled. B. Which ball takes longer to reach the bottom, or do they reach at the same time? And D. Find the ratio of their final speeds. A asks us to find the ratio of the two kinetic energies. Let's look at the case when the ball slides down the incline and doesn't roll. It starts with 0 kinetic energy, and all of its energy is in the form of potential energy, equaling mgh. At the bottom of the incline, the ball has no potential energy and all kinetic energy. Its final energy is 1/2 mv squared. That has to equal to its initial energy of mgh. Therefore, the final kinetic energy, 1/2 mv squared, is equal to mgh. Now let's discuss the case when the ball rolls down the incline. It still starts with 0 kinetic energy and all potential energy, and it ends with all kinetic energy. Its kinetic energy is equal to the kinetic energy of translation, 1/2 mv squared, plus the kinetic energy of rotation, 1/2 I omega squared. The moment of inertia of a sphere is 2/5 mr squared. Omega is equal to v over r. Therefore, the final kinetic energy is 7/10 mv squared. But it's still equal to the initial potential energy, mgh. Therefore, the ratio of the kinetic energies is equal to 1. When the ball slides, all the kinetic energy goes into its translational kinetic energy. When the ball rolls down the incline, its kinetic energy is divided up. Some goes into rotational kinetic energy, and some goes into translational kinetic energy. B asks which ball takes longer to reach the bottom. For the ball that slides, I know mgh equals 1/2 mv squared, and so I can solve for the final velocity as the square root of 2gh. For the ball that rolls, mgh is equal to 7/10 mv squared. So at the bottom, the ball that rolls is equal to 10 over 7 gh. The rolling sphere takes longer to reach the bottom. It has the same amount of kinetic energy, but its translational kinetic energy is less, so its center of mass is moving more slowly. Part D asks us to find the ratio of the final velocity for the sliding ball dividing by the final velocity for the rolling ball. On the previous slide, we found this velocity is the square root of 2gh, and this velocity is the square root of 10 over 7gh, so the ratio of the final velocities is the square root of 7/5. And the final question. At the heart of the Crab Nebula, in the constellation Taurus, is a rapidly spinning neutron star. This compact object has a radius of 10 kilometers and rotates with a period of 0.03 seconds. Astronomers have observed that its rotational period is gradually increasing at a rate of 10 to the negative seconds per day. Assume that the star has a mass twice that of our sun. A. Show that the rotational kinetic energy equals this constant times mr squared over t squared. B. Use this equation to compute the neutron star rotational kinetic energy. C. Show that the rate of change of kinetic energy is equal to this formula. D. Calculate the rate at which the neutron star is losing rotational energy. Here's a picture of a spinning neutron star. For part A, the moment of inertia of a sphere is 2/5 mr squared. Angular frequency is defined to be 2 pi over the period. Kinetic energy of rotation is 1/2 I omega squared. Plug in I, plug in omega. This is a way you can write the kinetic energy for a rotating sphere. For part B, we plug in all the given values. The kinetic energy of rotation for this neutron star is 3.49 times 10 to the 42 joules.
Oh my!
Good morning, ma'am.
Part C asks us to take the derivative of the kinetic energy. In reality, the mass, the period, and the radius are all changing. But to first order approximation, we assume drdt and dmdt equals 0, and it's easy to show that this formula is equal to the time derivative of kinetic energy. For part D, we plug in numbers and find that the neutron star is losing energy at a rate of 9.83 times 10 to the 31 joules per second. This is 1,000,000 times more energy than the output of the sun.
AcePhysics.org. Math and Physics Tutoring with Dr. Hudis.